So just like we talked about RC circuits and how the fact that it's alternating means that the current doesn't stop flowing after a while, we can now turn to LR circuits and do the same kind of mental understanding of the process. So we know that when you hook up an inductor in a DC circuit, what you get is, at the beginning, you get a very, very high voltage across it and no current flowing. And over time that changes according to Lenz's law. What we see in an AC circuit is constantly changing flux, constantly moving backwards and forwards. So we get a more complicated relationship. And just like we did before, what we find is that there is a part of the inductor that acts like a resistor. It acts to, reacts to the voltage. So we find that the voltage across the inductor is equal to I XL, where XL, just like for capacitor, XL is the reactance, and that is measured in ohms because it's the part of an inductor that's acting like a resistor. Okay, so far so good. What we then do is we can find out how reactance relates to the actual physical structure of our inductor, and we find that just like a capacitor, we can find that it varies according to the frequency. And I hope you can see that as the frequency changes either fast or slow, because the changing flux inside the inductor is what governs how its voltage and induced voltage changes, XL is also going to depend on it. And what you find is just like it was 1 over 2 pi f C, what you're going to get is 2 pi f L, where L is the inductance of the inductor measured in henries. And because omega equals 2 pi f, we can say that XL equals omega L. As omega changes, as the frequency of the power supply changes, so will the part of an inductor that acts like a reactor, the reactance of the inductor.